Hello everyone and welcome. My name is Jason Gregerson. In this video we're going to continue our discussion of linearly independent and linearly dependent sets of vectors. Specifically we'll talk about kind of the implications of the characterization of a set of vectors. We have two big results. One, independence will determine the uniqueness of solutions to AX equals B. So before we've defined independence, is meaning there's a unique solution, the trivial solution to AX equals 0, but we're going to carry this idea forward into the solution of non-homogeneous matrix equations. And then two, the concept of independence will help us identify the smallest set of vectors to span a space. Or another way of phrasing that is if we have a set of vectors and consider the span, we might be able to remove some of those vectors and not change the span. And the idea of linearly independence and dependence will tell us when we can do that and when we can't do that. All right, so let's talk about the first idea first, determining the uniqueness of solutions to AX equals B. So our statement is this: the columns of A are linearly independent if and only if there is at most one solution to AX equals B for any B in Rm. So at most one is kind of the important statement. That means there can't be more than one. That does mean there could be zero solutions. For the homogeneous equation, we knew there was always the trivial solution, but now that we have AX equals B, we're not necessarily guaranteed there will be solutions. And 0 is not more than 1. So this still satisfies the statement. So we could have 0 solutions, or we could have 1 solution, and that would satisfy at most 1. Basically, we cannot have infinitely many solutions. That's the case that we can't have here. So how do we establish that here through the idea of linear independence? Well, if our columns of A are linearly independent, what does this mean? Well, this would imply that we would have a pivot in every column of that coefficient matrix A. That tells us that there would be no free variables. And if there's no free variables, we can't have infinitely many solutions. So that tells us we must either have 0 solutions or 1 solutions. So let's look at a specific example just to see how that makes sense. Here we have this matrix, A equals 1, 2, 0, 1, 0, 0. And so if we want to solve AX equals B for some arbitrary vector B, we would create our augmented matrix that would look like this, augmenting with whatever these B values would be. Now I can look at those two columns, and since I have two columns only, and they're not multiples, I know they're linearly independent. So I have linearly independent columns, and if my B3 value was equal to 0, in that case I would have solutions, but because I don't have any free variables, I would have exactly one solution. I would have exactly one solution. And then if my B3 value is not equal to 0, well then that last row would be 0x1 plus 0x2 equals some number, which can never happen, in which case there would be no solutions. But because the columns are linearly independent, I can never have infinitely many solutions. So I would say that if there are solutions to this matrix equation, they would be unique. Now let's talk about the second big implication of independence and dependence. The next big idea is that independent vectors will help us identify the smallest set of vectors to span a space. So we're going to consider this set of vectors. I have a set of 4 vectors, and they all live in R3, and so I have plotted them in R3. So here I have my graph, and I've identified V1, V2, V3, and V4 on my coordinate system. So the idea is that all 4 of these vectors, well, they live at the x1, x2 plane. It kind of looks like the xy plane, but I'm using x1, x2, and x3 as my variables here. But all of my vectors live in that x1, x2 plane. And so if I thought of the span of these vectors, if I started taking linear combinations of these 4 vectors, I would never be able to leave that plane, and I could actually get anywhere I want to in that plane. So my 4 vectors span the x1, x2 plane, which means I should be able to take a linear combination of these 4 vectors and get to any vector that lies in the plane? Well, I'm going to represent any vector that lies in the plane as a vector b1, b2, and 0 for that z component. So no matter what b1 and b2 are, I should be able to take a linear combination of these vectors and get to v1, v2, v3. So now I look at my set of vectors, though, and I say, is that set of vectors linearly independent or linearly dependent? And it turns out it's linearly dependent. And one easy way I can identify that is I look at v4. It's 1, 1, 0. I can see that v4 is actually just v1 plus v2. I could take a linear combination of v1 and v2 and actually get to v4. And that tells me my set is linearly dependent. But not only that, it tells me that if I can represent any vector with v1, v2, v3, and v4, I actually don't need v4. Because whatever amount of v4 I used, I could simply replace with v1 and plus v2. So I don't need v4 to still span this x1, x2 plane. So let's get rid of it. So I'm just going to remove that vector from my set. Now I look at my set of 3 vectors. Is that set linearly independent or dependent? Well, it's still dependent. Because now if I look at v3, I say, well, v3 is actually just 2v1 plus v2. So I can visually see that v3 is just a linear combination of 2 other vectors in my set. That tells me that the set is still linearly dependent. And it also tells me that however I was representing this vector by using this v3 piece, I don't need v3. I could simply replace v3 with 2v1 plus v2. So I don't need v3, and I can still get to any vector in this play. Let's get rid of it. And so now I'm left with just v1 and v2. Now I look at that set of vectors. Is that independent or dependent? Now those 2 vectors are a linearly independent set. So this set is now linearly independent. I can see that because I have 2 vectors and they're not multiples of each other. Or because if I wanted to go through the process and throw them into an augmented matrix, I would have a pivot in every column of the coefficient matrix. So I know this set is independent. And I also can't remove any more of these vectors. I could not remove v2 and still get to everywhere in the x1, x2 plane. So if I have a linearly dependent set, there are vectors in that set that I could remove and not change the span of the set of vectors. So that idea and the uniqueness idea we previously talked about are both ideas we're going to build on and continue to build on in future sections. But we just want to tie them right now to this idea of independence and dependence. All right, that concludes this video. Thanks for your time.